We're going to pick up on chapter 8 and start learning some things about chemistry, how things change back and forth, how the reactions proceed. And in order to do that, we've got to understand numbers of atoms and molecules. We can't just go by mass. Even though Lavoisier showed us that masses of reactants, the total mass of reactants always equals the total mass of products. They didn't understand why. And it had no way to explain it, not until John Dalton came along. So let's share the PowerPoint. And one thing you'll notice is that the numbering on chapters is out of order. And the reason for that is, I think Zumdahl got it wrong. He put things in the wrong order, chapter order, in his book, because there are some things, some topics that he was discussing that in chapters 6 and 7 that weren't fully explained until he got into chapter 8. So I said, well, let's put chapter 8 first, and then 6 and 7 should make better sense. Besides, in my other chemistry courses, the progression of topics is more logical and in tune with those other courses if we approach it that way and put that chapter 8 first. So that's what we're going to do. We're going to look at chapter 8, share it, and turn it into a slideshow. There we go. Okay, so there's chemical composition. We'll have to, of course, define our terms, and those guys come later. So I wouldn't be too concerned about those chapters. Just focus on chapter 8. And these are the topics we're going to cover. Probably have enough time to finish them today. So, what do we mean by counting by weighing? Well, we have to, you shouldn't just do something because somebody says to. You need to understand something about why would we want to invent this type of counting objects by weighing them, right? Why don't you just count them? This seems like the long way around. If you have to count by weighing, why don't you just count them? Well, that's okay if you're counting cars, or you're counting marbles, or even if you're counting toothpicks that were knocked off the table and fell on the ground, like Rain Man did in that movie. It's okay as long as you can see what you're counting. But when you're counting atoms, you can't see them. So we need a different way to count the number of atoms. And we have to know the number of atoms and molecules in order to say anything about the way they react. Because it became painfully obvious in the first part of the 19th century that accounting for reactants and products purely on the basis of mass was not answering questions. It was not fixing production problems that chemists were experiencing in the laboratory and in the factory. So turns out you have to count the number of atoms in order to figure out why a reaction works. So we invented or they, our predecessors, invented this counting by weighing. Now, it wasn't anything new in the general scheme of things, but it was new for chemistry. So one of the conditions is the objects that you're counting don't have to be identical masses to be counted by weighing. In fact, the only way that you can count by weighing is to find the average mass of a number of objects. So you take a number, a subsample, find out how much that weighs, and then you find out what's the average weight of the individual object. Once you know that, then you know you have a conversion factor. So let's look at, okay, we're going to answer this question too. Count the atoms in a sample of a given element. By weighing, we have to know the mass of the sample and the average mass of the element. So let's take jelly beans, for instance. What's the mass of 1,000 jelly beans? Well, not all the jelly beans are going to have the same mass. They'll be pretty close, but they won't be exact. Our manufacturing techniques are not that good. But rather than count 100 jelly beans to find out what the mass is, why don't we just take 10 samples out of there, random samples, and find out what each one of them weighs. Or we could take 10 jelly beans and find out what the total weighs. But we'll do it this way first. So we'll find the mass of each one and find out that in this case, they do vary, right? They hover in the neighborhood of 5 grams each. And this way we can find the average mass of the jelly bean, right? Just add them all up and divide by the total number. And that's the average mass, which in this case is 5.0 grams. We could have counted 10 jelly beans and weighed all of them and found that they were 50 grams and divide 10 into the total and still found each one is 5 grams. So this method is the long way around. We could have done it a lot quicker and got the same answer. Okay. Now, how do you use that to find out what the mass of 1,000 jelly beans is? Well, what do we have now? We know that one jelly bean equals 5 grams. There's our equality. And if you have an equality, you also have a conversion factor. So what's the conversion factor? Well, it depends. What do we want to determine? Well, we're starting off with 1,000 jelly beans, right? 1,000 beans. We want to end up with so many grams. What's the mass? So we need a conversion factor. We want to cancel beans and leave us with grams. So that tells you which one of these is on top. We need 5 grams here per bean. Okay, so 5 times 1,000 is 5,000 grams, or 5 kilograms, right? So notice that we really don't have to find the average mass of the jelly bean in this case. We could have said 50 grams per 10 beans. 10 beans equals 50 grams, and use that. we get the same ratio. 50 to 10 is the same as 5 to 1. And you get exactly the same answer. Okay. Now I looked at this statement. I don't know why it just struck me today. This statement is kind of hard to follow. And it's difficult to place it in context until I consider one scientist, an Italian, so I'm not even going to read the statement. I'm just going to explain what this scientist proved and what a younger scientist did with his discovery, right? The man's name was Avogadro. And what he discovered was that if you have two vessels of exactly the same volume, so we're going to make them spheres. So those would be equal volumes. Okay. And we put gas in them, different gases in each one. You could put maybe neon in one and, I don't know, hydrogen in the other one. Doesn't matter, really. And he said, if the temperature is the same, the volume is the same, if the temperature is the same, and the pressure inside the vessel is the same, okay, then the number of particles in this one is equal to the number of particles in that one. And we use an abbreviation for that called N. Like that. Okay? So that was a monumental discovery. And it solved so many problems in the middle 19th century. It had to be interpreted, right? When he discovered it, he wasn't good at explaining himself. So it took another scientist, a younger scientist, to take that information and turn it into something useful. And if I can spell his name correctly, his name was Cannizzaro. I think that's how you spell his name. He was an Italian too. And there was this conference, big meeting in a place called, and now my mind's gone blank. It was a university in southern Bavaria, in Germany. It'll come to me in a minute. But the problem was in chemical industry was really gearing up in the middle to the, in the beginning to the middle of the 19th century, 1800s. And people were starting to really use what they knew about chemistry for research and for making money. Companies were springing up. But all they understood about chemistry was masses. They knew the mass of this and the mass of that made the mass of this, and they could sell that, make money. But if something went wrong with the reaction in the process, their chemical engineers couldn't figure it out. They didn't know how to fix the problem because they were approaching it from the wrong direction. They were approaching it from mass. And for chemistry to work, you have to understand atoms. How many atoms of each element are involved in the reaction, and what's their relationship to one another? Are they part of a compound? are the independent elements, right? And they didn't know that. It took this principle that Avogadro discovered and Cannizzaro's development to convince everybody that they were chasing the rabbit down the wrong hole. So, Karlsruhe, that's the place. Karlsruhe, Germany. It was a university there, and they were having a meeting. And all the greatest minds in Europe were there trying to figure this problem out. And most of the meetings they had devolved into not slugfests, but they were just off-track arguments, right? They couldn't stay on topic. And this fella, Cannizzaro, I think that's actually an A. Cannizzaro was a teacher. He was a number of things, but he was a teacher of chemistry. And he was having difficulty explaining things to his students because mass was the only thing that they had to go on. Well, he researched this topic and found that Avogadro had the solution to his problem. He couldn't convince anybody in the academic world to take him seriously. So he said, all right, I'll write a new curriculum. My students are going to learn it this way, right? The atomic way. So he wrote a curriculum and he published it. And he took copies of it with him to Karlsruhe. And he presented his paper. He presented his results and tried to convince the audience. Some of them were listening to him, but he had these copies. So he handed them out to everybody. So they could go away and stew on them for a while. And they realized eventually, some of them, that this solved all their problems. If they understood numbers of atoms rather than masses, they could fix their problems. In fact, Cannizzaro was credited by Mendeleev, who produced the first useful periodic table of the elements. Mendeleev credited Cannizzaro with helping him order his elements and put them in the periodic table in the correct order with the correct groupings. So now let's get back to our topic. I think that's what this slide was meant to say. So let's get back to counting by weighing. We'll look at this subject again when we get to chapter 15, I think it is, gases. All right. So let's say now we have a pile of marbles that weighs 394.8 grams. But we don't want to count the pile. But we can take 10 marbles that are representative, random sampling they call it. Sample the pile. Take 10 marbles randomly and weigh them. And we got 37.6 grams. How many marbles are in the pile? It's really pretty simple. You say, okay, you know how much they weigh, 394.8 grams. We just need to convert that to numbers, marbles. So we say, okay, we need to get rid of grams and leave us with marbles. So there's the definition of our conversion factor. Marbles on top, grams on the bottom. Well, we know that 10 marbles weigh 37.6 grams, right? 10 of these marbles weigh 37.6 grams. So you just divide this into that, multiply it by 10, and you got your answer. 105 marbles. Now, if you actually sat down and counted all those marbles, is there the slightest possibility that there could be 104 marbles or 106 marbles? Yeah, it's possible, right? Remember when we talked about error? There's always error in measurements. So if you made an error, if you made an error in one of these measurements, then you might be off in your count, but you'd be pretty close. So that's the same problem with atoms, right? If you know you have a certain number of atoms and then you weigh them, then you can find an average mass for the atom and use that information to count different masses of atoms. So what we need is a standard value for each element, right? Because Dalton said that everything's made of atoms, right? The elementary particle, but each atom's different. This element has a different atom than that element. And one of the differences is this one might weigh more than that one. Different masses for different elements. So we need some way to determine what's the mass of individual atoms. All right. All right, I've said this before. Atoms are so small that so scientists add a unit to avoid using very small numbers. Right? So instead of using the standard mass for something like grams, well, grams is derived, right? Kilogram is the fundamental unit. Gram is derived. But rather than use that, they decided in the beginning, we would say that one atomic mass unit was related to something. As it turns out, one atomic mass unit is approximately the mass of a proton. So let's not get there yet. What they needed was, let me see what's coming. I don't want to step on my own toes here. Okay, we'll get to it. Actually, that statement ought to come later. The mass unit of an element is actually the mass unit can be used for a number of different things. One is we can say we have, let's use carbon. It has 6 protons, and the most abundant isotope has 6 neutrons. So that means you have 12 mass number. 12 is the mass number. Okay, this also means that that atom of carbon weighs 12 atomic mass units. So that's 12 AMUs. So where does that mass come from? Most of it comes from the nucleus, right? Rutherford showed us that. Most of the mass of an atom is concentrated in the nucleus. And now we know that the nucleus is composed of both protons and neutrons, which gives us 6 plus 6 is 12 for the mass number. Okay. But all atoms are not alike. Some atoms can have different numbers of neutrons, right? If you change the number of protons, you got a different element, right? The atomic number is fixed for the element. So if you have 6 neutrons, then you have this isotope, we call it. If you have 7 neutrons, then you have this isotope. Okay? And you would think that this would be 13 atomic mass units. And if you thought that, it would be a logical conclusion, but you'd be wrong, right? Because this may be the number of protons and neutrons, but it's not the mass of the whole atom. What we need is a standard. We have to fix a point of reference, and everything else is referenced to that point. And in fact, this is that point. Carbon-12 isotope is the point of reference for all atomic masses. And we fix, by definition, that isotope, that atom of that isotope, weighs 12 atomic mass units. Infinite number of zeros. Everything else is compared to that. So when you compare this atom, which has 6 protons and 7 neutrons, that's the mass number, that's true. But the mass of that atom of that isotope is not 13. It's probably 13 point something bigger than 13, just a little bit bigger. Right. I know it's a fine distinction and it sounds like I'm splitting hairs, but what I'm saying is that this is our reference point, carbon-12 isotope. Okay. But if you look at the natural abundance of isotopes, you still have some of these 13s in the natural mix, and they will skew the average mass of carbon, not just the isotope, but the average mass of naturally occurring carbon is a weighted average. So most of them are 12. So if you look at your periodic table, the average atomic mass of carbon is 12.01. Well, actually, that's rounded off. It's 12.0111. So how do we calculate the average atomic mass, which is really the one that's most useful to chemists, because we're not dealing with individual isotopes. Right? Isotopes behave almost identical in a chemical reaction. So we really don't care about the isotopes in a chemical reaction. We care about the average atomic mass. That's something that we can use when we're doing calculations in chemistry. Okay. So once we know that that average atomic mass, how much does each atom weigh? If we have a mass, then we can find out how many mass units represent that collection that we've identified. So if we have the 431 atoms of carbon, what is the mass in atomic mass units of that total collection? Well, if you have 431 atoms of carbon, you need a conversion factor that will get rid of atoms and replace it with atomic mass units. So for each atom, on average, in naturally occurring abundance of all the isotopes of carbon, you have 12.01 atomic mass units per atom. Right? That's an average. Now, just for argument's sake, what's the probability that you will, if you are able to remove one at a time, one atom at a time from a large number of carbon atoms, what's the probability that you're going to find one that weighs that much? 0, because it's a weighted average. You're not going to find one. At least the probability is approaching 0. Let's put it that way. Okay, so if we multiply 12.01 times 431, right, then we should get 5,176 atomic mass units for that collection. But that's kind of, atomic mass units is okay for physicists and physical chemists to deal with. But most chemists need a more practical approach because we don't have a balance that will weigh anything in atomic mass units. It just doesn't exist. Our balances are calibrated in grams, usually, and fractions of grams. So we need a different understanding of atomic mass, average atomic mass. And we're not going to get there in this slide. Let's see. All right, this is just another problem of the same kind. Aluminum, if you look up aluminum on the periodic table, then you find that it's 26.98 atomic mass units average for that atom. So in that case, you can make a conversion factor, just like we did for carbon, and discover that if you have 75 atoms, then you're going to hold in your hand, so to speak, 2,024 atomic mass units. Well, as it turns out, the atomic mass unit is extremely small in terms of grams. So you're going to have a huge amount, lots of atoms, to have enough of them to weigh on a balance in your laboratory. So we need a number of them, a standardized value, a number that we can work with. And that value in chemistry is called the mole. And the mole is defined as the number of carbon atoms in 12.01 grams of carbon, naturally occurring carbon in the Earth's environment. 12.01 grams will give you 1 mole of carbon atoms. So how many atoms is that? Well, there's a number attached to it, and it's refined over the years. For our purposes, this estimation, this 6.022 times 10 to the 23rd is a mole. and it's given Avogadro's number. I mean, he didn't determine the mole, that number, but it was his principle, his law, that allowed that number to be determined. So now 1 mole is fixed at 6.022 times 10 to the 23rd units of anything. It could be individual atoms. It could be diatomic molecules of an element. It could be molecules, say, of water or carbon dioxide. Or for that matter, it could be chickens. A mole is just a number of units. So the significance of that number is that, as it turns out, if you have 1 mole of carbon atoms, you have this many atoms, and if they were derived from naturally occurring carbon in our environment, then a mole of those atoms will weigh 12.01 grams. Okay, so now if we look back at the periodic table, we find that we were talking initially about 12.01 atomic mass units per carbon atom. Right? But that number can also represent 12.01 grams carbon per 1 mole. And we abbreviate mole by just dropping the E. So that's good, because that number is also represents something that we can deal with, something that we can use. Okay. So that conversion factor could either be moles on top or moles on the bottom. Doesn't matter. They're equivalent. 1 mole equals that value, which means your conversion factor can be moles on top or moles on the bottom. Doesn't matter. Now, we're saying carbon atoms here, but actually it could be aluminum atoms, or it could be water molecules. That many water molecules is 1 mole. Right? They'll have different masses, of course, because they're composed of different elements. But for counting purposes, a mole is that number, and that's it. Now, over the years, chemists who are interested in this topic will refine the number experimentally, but it never affects the first 3 digits, the first 3 decimals, 0 to 2. That's always the same. The changes that they incorporate into new estimates of a number happen in like the 5th, 6th, 7th, 8th decimal place. So it won't affect us at all. That number, for all intents and purposes, is fixed. Okay. So what we find is that aluminum with that many atoms in it will weigh this amount. And that's the atomic mass in the aluminum's little square on the periodic table. And look at any of them. So why is this difference right here? If you have the same number of atoms, why is it different? Because each atom weighs a different amount than the other element. That's the difference. And remember, all of this is referenced to carbon-12 isotope. So for the carbon-12 isotope, you would have 12.0000000 grams of carbon-12 per mole. That's the standard. initially we said it was so many atomic mass units per atom. And that's true. But now we can say it's that many grams of carbon-12 isotope per mole of carbon-12 isotope atoms. Okay. So if we were to put two different gases in those spheres that Avogadro was talking about, and we know we have exactly the same number of molecules or atoms in each sphere, at the same volume, at the same temperature, at the same pressure, and we have the same number of particles. Now, that little n is the abbreviation for moles. Right? It's not the same as this little n. That little n means neutrons, right? But n by itself is used to represent the number of moles of something. So if that's the case, and we have two different gases here, say we have hydrogen on this side and helium on this side, how will the masses compare? Which one will be heavier? That one. Because helium atoms weigh more than the dihydrogen molecule. This dihydrogen molecule, for a mole, weighs 2.02 grams per mole, while the helium weighs 4.00 grams per mole. And the reason is, or 4.00 atomic mass units per atom, or 2.02 atomic mass units per molecule. But the difference between the two, the mass difference, is attributed to the difference in mass of individual atoms. And that's the same for any element. And that's why this was such a breakthrough in the late 19th century. Because now we could compare equal numbers of atoms. Started off with gases, right? Because that was the basis of Avogadro's law. Started off with gases and compared masses, right? But eventually it progressed to equal numbers of liquids and solids. Once they figured out how to make the measurement of equal numbers, then they could determine the relative masses based upon carbon-12 isotope. So now we have atomic masses for every element in the table. I mean, even the radioactive ones and the man-made ones. All right. So, can we determine the number of copper atoms in a 63.55 gram sample of copper? What's the question? The number of copper atoms, right? We want to know that number of copper atoms. And we're given 63.55 grams. So how do you get from there to numbers of copper atoms? Well, we don't have a direct conversion from grams to atoms. We can go from grams to moles. we can go like this, and then we can go from moles to numbers. Okay, we can do that. So we need this value, right? So what is that value? Whenever you see a quotient where the units are grams in one position and moles in the other, it could either be grams on top or moles on top, it doesn't matter. When you see that quotient, light bulb goes off in your head, or a bomb, or whatever it takes. Think atomic mass. And look at your periodic table to find the value. Grams per mole, moles per gram. So we look for copper. Copper's a transition metal, right? It's right here. And we look and see it's 63.55. So if you have in your possession 63.55 grams of copper, you have 1 mole, right? Well, mathematically, these two cancel, and that one times this one gives you 6.022 times 10 to the 23rd atoms of copper in that sample. All right? So, which of the following is closest to the average mass of 1 atom of copper? Well, logically speaking, you're going to say that if this is 1 mole, right, 1 atom can't be that mass, right? Because that's 6.022 times 10 to the 23rd atoms to give you that mass. And by similar logic, all of these masses are just way too big for 1 atom. So this is really the only one that works. But how did we get it? Well, there's how you get it. You start off with 1 copper atom. Right? Instead of writing it on the board, let's see, annotate. Let me do a line here. So you're starting off with this 1 copper atom right there. And you want to find out mass. Well, the mass of copper is related to its molar mass, or atomic weight. So eventually we've got to get to this one right here. Let's see. We got to get to this conversion factor right here to give us grams. But in the process, we've got to convert the 1 atom into how many moles that is, because that's the conversion factor that we need to give us mass. So we go in here and we say, okay, we're going to convert 1 atom to how many moles that is. Right? So how many moles is it? Well, the multiplier here of 10 to the 23rd is in the denominator. So in the numerator, it'll be 10 to the minus 23rd. Right? And then it will be multiplied by the reciprocal of 6.022. So you just take the reciprocal of that times 10 to the minus 23rd, or you just plug it in your calculator, right? And there's 1 and there's 1, so this is still the reciprocal. Plug it in your calculator, hit the reciprocal button, and multiply it by 63.55 grams. And if you do that, you end up with this value. 1.055 times 10 to the minus 22nd grams is the mass of 1 carbon atom on average. you won't find one carbon atom with that exact mass, because this is an average calculation, right? Keep that in mind. We have to count by weighing, and when we do that, we inherently introduce averaging error. All right. So let's go to the next slide. I know what's wrong. There we go. Okay. How would we do this one? Calculate the number of iron atoms in 4.48 mole sample. That's where you're starting. And the question is, how many atoms is that? So if you're going to have atoms over here, right, you need a conversion factor that will cancel moles of iron and leave you with atoms. So what's the number there? Avogadro's number. So many atoms per mole. Right. Multiply that together and you get 10 to the 24th iron atoms. Let's see. Okay. All right. What about this one? A sample of 26.98 grams of aluminum has the same number of atoms as how many grams of gold? Well, what does that represent? 26.98 grams of aluminum. All right. I have a hunch. Look at the periodic table at aluminum. 26.98 grams is 1 mole. So you got 1 mole of atoms. Right. So how many grams would a mole of gold weigh? Because if you have the same number of atoms, both is 1 mole. So you look at gold right here. And it looks like it's rounded off 196.97. Okay, they're rounding it even further. 197. Right, so there's the logic. If you got a mole of each, then the gold is heavier than aluminum, so each atom has to weigh more, which gives you a different atomic mass, average atomic mass. We didn't do in this class, no. We didn't do a weighted average calculation. I think that's just because this is an introductory course. But weighted averaging is very similar to the way that you would determine your grade point average, right? If you get an A in a course that's worth 3 credit hours, that boosts your average more than if you get an A in a course that's only 1 credit hour, right? So you know how to do that average. It's a similar process for average atomic mass of naturally occurring isotope mixtures of the elements. You weight them. And the isotope that is the most abundant is the major contributor to the average atomic mass. Okay, how about this one? Which of the following 100-gram samples contains the greatest number of atoms? All right, let's do that. We've got magnesium, zinc, and silver. Magnesium, zinc, and silver. Okay. 100-gram samples of each. So the question is, how many atoms does 100 grams of each represent? Okay, so with a problem like this where you're comparing things, I like to channel Henry Ford, assembly line. If you do it this way to make one version of car, then you go back and do it this way to make a different version, but the steps are the same. You just change some of the parts along the way. Same steps get you to the answer for each one. So how would we convert this to the number of atoms? The only relationship that we have that takes us to numbers is moles to mass. So grams would be on the bottom to cancel it, and moles on the top. Okay. So you have to find the molar mass of each element. Right? So you have silver, 100 grams is 107.97. Okay. And zinc is 65.39. And magnesium is an alkaline earth, so it's over here in the second column, 24.31. Okay. So now we got moles. We could make atoms, right? We could calculate atoms, but do we need to, right? Once we get to moles, that's counting. That's a unit of measure of numbers of atoms. So we really don't have to say how many atoms there are if we're only going to put them in order, or which one contains the greatest number, right? So look at this. 107 divided into 100. What is that? That's less than 1, isn't it? So this answer would be less than 1. How about this one? 65 into 100, right? If it were 50, it'd be 2. But 65 means less than 2. It's less than 2, but greater than 1. Okay? How about magnesium? 25 into 100 is 4. So 24 into 100 is more, 24 into 100 would be greater than 4. Right? And that's in terms of moles. Now we could have done the calculation, sure. But I'm thinking, if you're in the middle of a test, you want to get the answer. Right? You don't want to dilly around and fritter away your time. So this gets you to the answer. We know we have a comparison of moles, right? This one's the least number of moles. This one's the next one, and that one's the greatest number of atoms. Right? So what we're saying is the greatest number of atoms, if the masses are the same, then the greatest number of atoms is going to be the element with the smallest average atomic mass. Right? This is a smaller atom than that one is, and this is a smaller atom than that one is. So it takes fewer of these to make the same mass. It takes more, a little more, to make this one, and takes a lot more for that one to make the same mass. That's why when auto manufacturers want to save weight, then they alloy iron and steel, alloy it with magnesium, because magnesium's lighter than iron. You don't want to put too much in it, of course, because then you destroy the strength of your steel. But magnesium is also used as an alloy in aluminum to produce a reasonably strong version of aluminum that can be used in airplanes because it's light. In fact, magnesium is lighter than aluminum, but it still retains, in fact, it improves the strength of aluminum. Okay. So let's make room for some more stuff. Okay. How about this one? Rank the following greatest to least. So the most number of atoms to the least number of atoms. In this case, we don't have to do much of any calculations at all. So if we have 107.9 grams of silver compared to 70 grams of zinc and 21 grams of magnesium, we want to rank them in order. We need to look at their average atomic mass. If you got this many grams, we want to rank them in order of numbers of atoms. We just need to know the numbers of moles of each, just like the previous problem. So 107.9 grams of silver is what? That's exactly 1 mole. That equals 1 mole. How about 70 grams of zinc? Well, let's see, zinc is 65.39. So that's more than a mole, correct? Greater than 1 mole. And 21 grams of magnesium, we found that magnesium is 24.3, is it? Yeah, 24.3. So that's less than a mole. Doesn't have enough mass to give you a complete mole. So now we got our ranking, right? We want to put them in order from greatest to least. Greatest is, that's greater than a mole. And this is exactly a mole. And this is less than a mole. So now we have them ranked in order. Well, I actually did the calculation here, but you don't have to. You just need to know what's their relative order, because that's all that's asked for. And BAC is the same as zinc, silver, and magnesium in that order. Okay, so let me see here. So this is the author's idea of problem-solving techniques. Where are we going? Read the problem and decide on the final goal. What that says to me is, what's the question? Right. You got to know what the question is, or you'll never get the right answer. So that's what you're looking for, and especially in a word problem. What is the problem asking? Then you say, all right, what do I need to get there? I need a plan to get to the answer with the information that I'm given. Or if I'm given some information, but I'm not given all the information I need. Can I find it? If you have a periodic table, you can get a lot of information from that. If you have access to the useful information that I provide at the end of your review documents, you'll have that available. You'll also have that available on exams. So it might be well to go look at that and work some of those problems. And then once you've answered the question, you think, do a reality check. Does your answer make sense? Like that question, that earlier question. What's the average mass of an atom? I think it was copper, wasn't it? Well, if you look at the answers, if you had given an answer that was 50 grams, then that should say that doesn't make sense. No atom weighs 50 grams. So you go back and check yourself. Okay. So this is what we call the molar mass. The mass in grams of 1 mole of substance. And it's not just for elements, right? On the periodic table, yes. Those numbers at the top of each square in this version of the table, those numbers are the mass, average mass of 1 mole of that atom, of that element. But molar mass can also be applied to compounds or diatomic elements for that matter. Remember all the diatomic gases? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine. Those are all diatomics. So once you find the atomic mass of each atom, you have to double it for the molecule. Same logic for compounds. If you know, for instance, if you know the formula is this for water, right? 2 hydrogen atoms, 1 oxygen atom in that molecule, then the molar mass of water, 1 mole of water, right? There's a 1 out here. 1 mole of water is 2 hydrogens and 1 oxygen. Per mole of water. Okay, simple. Just add up the molar masses of each of the atoms. And you have to keep, I mean, if there's 2 of them, you better double it. Or if there's 10 of them, you better multiply it by 10, whatever it takes. Nitrogen, of course, straight off the periodic table, 14.01. Water, we just calculated that one. Right? Oops. What was that doing here? Oh, okay. Yeah. 1.01, I rounded off to 2 places. This is 3 places for hydrogen, plus the 1 oxygen atom. Down here, you've got barium nitrate. So barium, where's barium? Well, barium's in the 2nd column. It's an alkaline earth metal. So you look at that value, you got 1 of them, that's all you need. How do you know that you have 2 nitrogens, 14.01 per nitrogen? Well, the subscript here propagates through the entire parentheses. So if you have 2 nitrate polyatomic ions, then you have 2 nitrogen atoms. And 2 times 14.01 is the contribution of nitrogen. The contribution from oxygen is 2 times 3, which is 6. So 6 times 16. Okay, in that case, you add them all together and you've got a pretty heavy unit here, formula unit. Okay. So this you can memorize this if you want, but I'm saying, why don't you use dimensional analysis to find the answers that you need? Moles of a compound is mass divided by molar mass, right? So if you take the units, just take the units of measure. Moles on this side is supposed to be what? Grams on this side divided by grams per mole on that side. Okay? So in an arrangement like this, mathematically speaking, the numerator in the denominator, the numerator of this expression in the denominator, that is in the denominator, right? So it will cancel the numerator here. But the denominator of the denominator is a numerator. So this one is actually like that. That's why that formula works. But if you want to know the moles of a compound, I'm saying depends on where you start. If you start with mass right here, you start with grams, and you want to know moles, then you do that. If you have X grams, then you need a value in here for whatever this is. And these cancel and leave you with moles. I think that's more logical, dimensional analysis wise, than just to memorize the formula. Okay? All right, what's the molar mass of nickel 2 carbonate? How are you going to find the molar mass of a name? You can't. You've got to have the formula before you can do the molar mass. So if you got the name, you got to be able to write the formula. That's why I hammered that early. You need to learn how to write these formulas and practice them. Nickel. The name says it's a 2+ charge, right? Why would it say that? Because nickel is a transition metal, and it can have more than one charge. So that one has a 2+ charge. What's carbonate? There's no element in the periodic table, carbonate. There's carbon, but if you use carbon only, you'll get it wrong. Carbonate is a polyatomic ion. So you'll also have that table, the polyatomic table, derived from the useful information. I don't have it with me. But you look up carbonate and you find its formula, CO3 with a 2- charge. Okay, so this unit behaves as a single ion with a 2- charge, balances the 2+ of this nickel. So that means the formula is this. That's it. Now you can find the molar mass because you have the formula. So what's nickel? Well, let's see. Let's look for nickel. Nickel is right over here, 58.69. grams per mole of nickel. Carbon, 12.01 grams per mole. 3 oxygens. So what's 3 times 16? 48. Now you add them together. 18. Carry your 1. I think that's right. 118.7 grams per mole of compound. Okay? Now see if the slide agrees with me. 118.7. Yep, it agrees. Doesn't mean it's right, but we agree. Should be right. If you do it right, you get the right answer. Okay. How about we have equal mole samples, equal numbers of each of these compounds? Dinitrogen monoxide, aluminum nitrate. Why didn't I say aluminum 3 nitrate? Because aluminum is a fixed charge. It's a type 1 compound. You don't have to say aluminum 3. If you say aluminum 3, you're redundant. And chemists hate redundancy almost as much as ambiguity. So aluminum nitrate means nitrate is a -1 charge on a polyatomic ion, so you need 3 of them to balance the aluminum. That's why it's written that way. Potassium cyanide. Cyanide is a polyatomic ion with a -1 charge. Potassium is an alkali metal with a +1 charge. So we want to rank these from least to most number of nitrogen atoms. Okay. So I smell Henry Ford. We're going to set this up in assembly line process. So we've got what? Dinitrogen monoxide. We have aluminum nitrate. And we have potassium cyanide. And we want to rank them from least to most nitrogen atoms. If we have 1 mole samples, equal mole samples of each, and we're going to assume 1 mole. It doesn't have to be 1 mole, right? It could be 2 moles, but since we're ranking them in order, if we use equal mole samples, no matter how many moles you choose, you're going to have the same rank. So let's keep it simple, just 1 mole. So if we've got 1 mole of each, right? Numbers of nitrogen atoms. This is 1 mole of compound. Okay? What do we have here? We have a mole of compound. And we have a certain number of nitrogen atoms, certain number of nitrogens. Right? And if we find the moles, we found the number of atoms, right? It's still a counting number. So this has 2 nitrogens per mole of compound. This one has how many? 3 times 3 is 9. 9 nitrogen atoms. And this one has 1. So what do we have here? We have 1 mole of nitrogen atoms. We have 9 here. And we have 2 here. So from least to most is potassium cyanide, then dinitrogen monoxide, then aluminum nitrate. Which would be, which one? This one. C. Okay? Now, how can we complicate this even further? Give you a mass of each one. Say, so much mass of dinitrogen monoxide, so much, a different mass of aluminum nitrate, and a different mass of potassium cyanide. Then what would you have to do? You'd have to find out actually how many moles of each compound you have first, and then the ratio of moles of compound to moles of nitrogen. So that looks to me like we're going to do it for these compounds. Okay, so we have 100-gram samples of each. That's nice of them. Water, dinitrogen monoxide, C3H6O2, C3H6O2, and CO2. All right. Well, we're pretty familiar with these. Water, dinitrogen monoxide is what? Laughing gas. That's nitrous oxide. The trivial name is nitrous oxide. The systematic name is dinitrogen monoxide. This one, we don't know exactly, but it looks to me like it's propionic acid. And this one, of course, is carbon dioxide. But we got 100 grams of each. That's where we start. All right. So we got to convert to moles of compound first, don't we? Before we can compare the number of oxygen atoms, how many moles of compound do you have? Right? So we need assembly line. Get rid of the grams and leave us with moles. Right? So how about water? We did that one before. That one is 18.02 grams per mole. Dinitrogen monoxide. All right. One nitrogen is 14.01. Two is 28.02 plus water, 16. 44. Sometimes my brain doesn't work too well. Yeah, 4402. Okay, how about this one? Well, 3 carbons, 12.01, 6 hydrogens, each 1.01, so that's 6.06, right? And then 2 oxygens at 16 each is 32. So that one's 74.09. Okay, per mole. And carbon dioxide is 12.01 for carbon, because we only have 1 of them, and 32 for the oxygens because we have 2 of them. That's 44.01. Okay. Now, we have moles of compound. Before we do our calculation, why don't we introduce a chain conversion and take moles of compound to moles of nitrogen. So this will be nitrogen on top and the compound on the bottom. And this moles and moles. Oops. All right, so how many? Oh, excuse me, I'm thinking nitrogen, right? That's not even the question. Oxygen. There we go. Oxygen atoms. So in this one, we have 1 oxygen for every mole of water. The ratio is 1 to 1. Here we have 1 to 1. Here we have 2 to 1. And here we have 2 to 1. Okay? So now we can do the calculation. Just go right on through. So 100 divided by 18.02 times 1 is 5.54. Moles of oxygen. Okay, how about this one? 100 divided by 44.02 times 1 is 2.27. How about this one? 100 divided by 74.09 times 2. 2.70. And the last one, divided by 44.01 times 2, 4.54. So, with 100 grams of each, the number of oxygen atoms is greatest to least. This is the greatest. Next is this one. Next is this one. And last is this one. Okay? And those are the calculations right there. Now in this one, I actually calculated the atoms, which you don't need to do to put them in order. Right? So there's the order. And there's the question. Do you really need to calculate the number of atoms? No. Once you've got a counting unit for numbers, then to answer this question, you don't need to know the number of atoms. Not if you're putting them in order. If the question is how many oxygen atoms are in one or the other, then yeah, you would have to calculate the number of atoms. And then you would take this mole of oxygen here and convert it to number of atoms using Avogadro's number. All right. What's next? Let's see. Let me look at my hard copy and see how we're doing. Yeah, we're going to make it. Okay. How many grams of fluorine? Notice that what we're doing here is dimensional analysis. Conversion factors. I'm pretty sure I said at the very beginning, a lot of, it's good to understand the chemistry. I mean, that's our goal, understand chemistry. But the actual calculations after that understanding are done by conversion factors. Learn how to use conversion factors and you're 90% of the way there. It helps you analyze problems too, if you understand how the conversion would take place. Okay, how many grams of fluorine are contained in 1 molecule of boron trifluoride? There's your molecule, boron trifluoride. And what's the mass of one molecule of that? Okay. So we have one molecule. That's where we start. And we want to end up with mass in grams. So, how much does a molecule weigh? We don't have a conversion that goes directly from molecules to grams. We have one that goes from moles to grams, right? So if we convert this, how many moles does one molecule represent? Molecule. To cancel that, we have molecule. I misspelled it. There we go. One molecule. Actually, that's not right. One mole is represented by 6.022 times 10 to the 23rd molecules. There you go. So one mole equals that many molecules. That's canceled. Now we can do moles to grams. We just need to know what's the molar mass of boron trifluoride. So we look it up. Here's boron right there, just above aluminum, which is 10.81 grams per mole. And fluorine is 3 times 19.00, rounded off. I'm still there. So what's that value? 57, 19 is times 3. Yeah, 57 plus 10.81 is 67.81. There you go. Now, if we multiply that and then divide by this, Avogadro's number, I get, let's see, looks like both of them have 4 significant figures, 1.126. Ten to the minus 22 grams. That's how much one molecule of boron trifluoride weighs on average. Okay, let's see, is that what it says? What did I do wrong? Oh, that's not the answer. The reason I got the wrong answer was I was answering the wrong question. How many grams of fluorine are contained? All right, so I got to redo it. Get rid of my cheat there. And nobody stopped me. Okay, one molecule of BF3. So one molecule BF3 has how many atoms of fluorine? There you go. Now we got rid of that one. Now we're down to atoms of fluorine. So 3 atoms of fluorine you have 6.022 times 10 to the 23rd atoms is 1 mole. Okay. Then you can do 1 mole is 19 grams. Now I'll get the right answer. So we have 3, because that's 1, 3 times 1, divided by Avogadro's number, multiplied by 19. 9.465 times 10 to the minus 23. Okay. Yeah, now we're cooking. All right. So at the beginning, this chapter was identified as chemical composition. Now we're actually going to get to a discussion of chemical composition. Okay. Very often, composition of compounds is expressed in terms of percentages. All right, I've mentioned before, percentage is a dimensionless number. You have to know if it's parts per 100. Parts per 100 parts, what does the parts mean? Well, in terms of percent composition of compounds, we're talking about grams per gram. It's mass. So we say percent mass. And that nails it down. Now we know what the percent means. But how do you determine that? Well, all you need is, for the mass percent of an element in a compound, all you need is the mass of the element and the mass of the compound. So if you have this much mass of the compound, how much of that mass is represented by the element? And then do the ratio. That's usually how chemists on the bench determine composition and express it in percent mass, percent by mass. But you can work back the other way too. If you know what the formula of the compound is, say it is known, then you can calculate a percent by mass composition. All you have to say is, let's do an example. Let's take water. What's the percent composition of oxygen in water? Well, you know that if you have 1 mole of that water, that's your total amount of water. 1 mole is 18.02 grams per 1 mole. Well, in that mole of water, how many moles of hydrogen do you have? You have 2 moles of hydrogen. So it's 2 times 1.01 grams per mole, and then times 100 to make percent. Oh, that's hydrogen. What am I thinking? I said oxygen, didn't I? 16.00 grams per mole. Okay. So these units cancel. Same there, right? That's why I call it a dimensionless number, because there are no units left over after you cancel them. So what is that value? 16 divided by 18.02. %. Oxygen. Okay, that's how you would calculate it from the formula. Well, if we know how much oxygen is, what percent is hydrogen? It should subtract that from 100, right? Because hydrogen is the only thing left. So whatever else is left over has to be hydrogen. So we subtract that from 100, and we get 1, 2, let's see, 8 times 1. 11.21% hydrogen. Let's see if that adds up. Yeah. So we could do it for iron oxide also. Iron 3 oxide. Right? You have to know the formula before you can do this. And iron 3 oxide is Fe2O3. So you take the iron portion, which is 2 times the molar mass of iron, and you put it in the numerator and the denominator because it is part of the whole. Right? This is the whole. That's hydrogen plus oxygen. This is the iron contribution. Now we need to add the oxygen to it. There it is. So this is the total, and this is just the element that you're interested in. And it's 69, almost 70% iron in iron 3 oxide. Okay. How about this one? Morphine. They tell me morphine works great on some types of pain, but on others it won't touch it. So that's beside the point. What percent by mass is the carbon in this compound? Right? So how would we approach that? Well, we would say if it's C17, H19, NO3, we would say percent is carbon in the numerator and the denominator both, right? How many carbons do you have? Well, you have 17, right? So it's 17 times 12.01 and 17 times 12.01 plus, now you add the hydrogens in, 19.19. Why did I say that? 1.01 times 19 is 19.19. And then you add the nitrogen, 14.01, and then you add the oxygen, 3 times 16, right, times 100. So that's how you set it up. This is the total, so it has to include both this much of our element of interest, has to be in top and bottom. And that gives you 71.6% carbon. Okay. Okay, so we're back to 100-gram samples of each one of these compounds. Rank them highest to lowest percent oxygen by mass. All right. So, water, laughing gas, propionic acid, and carbon dioxide. So we want, let me read that question again. Percent oxygen by mass, highest to lowest. Percent oxygen. Okay. So we've got 100-gram samples. So we could do this two different ways. A 100-gram sample gives you how many grams of oxygen? But if we're going to rank them highest to lowest percent oxygen by mass, the sample that you're given is irrelevant. Doesn't matter, because it's going to be a percent eventually anyway, right? If we determine the grams of oxygen in this 100-gram sample, then that would be percent, right? Parts per 100. So we could do that, but why don't we just calculate the percent? Okay? So we just say oxygen, 16, divided by 16 plus 2.02 times 100, right? 2 times 1.01 for hydrogen. And this one is 16 in the numerator, 1, 1, 1, 1, 16 in the denominator, and 2 times nitrogen times 100. Okay. This one, we've got 2 oxygens, so we'll have 32 in the numerator and 32 in the denominator, plus 3 carbons plus 6 hydrogens times 100. And this one, oxygen, is also 32. Plus 1 carbon times 100. Okay? So what do we get? 16 divided by 18.02. Is 88.79%. Oxygen. How about this one? 16 and add 28.02, right? 2 times 1401. Then divide that into it, times 100, 36.35. Then propionic acid. Let's see, 36.03 and 6.06. $43.19. And last one, carbon dioxide. $72.71. Okay, so order these in highest to lowest. All right, this is the highest one. This is the next one. This is the next one. And that's the last one. Okay, what this also illustrates is if you try to react, say, I don't know, well, you couldn't react these two, any of these two easily. But if you tried to react these and you were focused on the oxygens as a principal component, and all you knew was mass and percentage composition, you would be lost trying to decide how these compounds interacted with one another, because they don't interact on the basis of mass. They interact on the basis of numbers of molecules and atoms, right? What Dalton said, during a chemical reaction, what happens? Atoms are neither created nor destroyed. That's the law of conservation of mass. The reason is that they're just rearranged. Just move them around, right? So chemists in the 19th century knew that, right? Because Dalton's law preceded them. They just didn't know how to figure it out. It wasn't until Avogadro and Cannizzaro figured it out for them that they could eventually fix their problems. Let me see if there's another one that needs that data. No, we're going to do empirical formulas now. Okay. You can use this percent composition by mass to determine the empirical formula of a compound. Now I have to define empirical formula, don't I? All right. So what is an empirical formula? Well, we have written formulas for compounds. And you could write, if we're just interested in the ratio of atoms in a compound, then you could write water like this. Right? But that may not be water. We know water is H2O, but the empirical formula for this compound would be H2O, whether it was water or not. Now, depending on its behavior, its physical and chemical properties, we would be able to tell that one was water and the other is not. But empirical formula doesn't tell you that, because they both have the same empirical formula. It's like this one. That's benzene, right? But how about this one? That's acetylene, right? Benzene and acetylene, two entirely different compounds. I mean, they're both flammable, of course, but their empirical formula is the simplest whole number ratio of the elements in the compound. So these both could be represented by that empirical formula. Now you're probably asking yourself, how does that help? Well, it's a step on the way to understanding. When we have percent composition by mass determined experimentally in the lab, we can use that information to derive an empirical formula for a compound. Okay? That's only part of the way, because what we really want to know is what's the molecular formula for the compound. And to do that, you need an additional piece of information. And I'll cover that in just a second. Okay. I just said that. So what we've got is, say, if we have this as our, say we know that's the molecular formula. This is the empirical formula. Oops, not N, H. How would we represent this in terms of conversion? We need a multiplier down there. So this would be a 6, multiplied by that is 6, multiply that 1 is 6. So then if we knew this value, then we could get the molecular formula, right? If this were 6, then we could derive that from it. Okay, so that's what we're looking for, a multiplier for the empirical formula that will give us the molecular formula. All right, so that's what benzene would look like. Let's take an example, right? That's the best way. I mean, you can follow rules, a recipe, but an example, I think, explains it better. So let's take this example. We're given a gaseous compound containing carbon and hydrogen. So we have carbon and hydrogen. And we know that that's it. That's all there is in the compound, right? How do we know that? Well, you do a qualitative analysis first to determine what elements are present, right? It can be simple or it can be very complex. Actually, nowadays, there are some analytical quantitative techniques that determine how much is there plus what is it, right? So the earlier version I was giving you was wet chemistry in the past. Now we've got modern instrumentation that will do both at once. Okay, so we have carbon and hydrogen in our compound, and we find that 83.65% is carbon. So how much hydrogen is it? Well, whatever's left over, right? So this would be, let's say, 5 and 3 and 6 and 1. Right? Let's see, add that up again. Yeah, that adds up to 100%. Now, how do you determine the empirical formula from that? What are we looking for in an empirical formula? We're looking for the ratio of atoms in the molecule. This is a ratio of mass. We want the ratio of atoms. So you've got to convert this ratio into atomic ratio. But what did I say about this? That's a dimensionless number. There's no mass there, really. So how are you going to convert mass of this element into numbers? Right? We could do that if we knew the mass. Right? We just use molar mass, grams per mole, moles per gram. And if we knew how many grams it was, we could convert that to moles. And the mole ratio is the same as the atomic ratio, right? Because we're counting numbers. So here's how you do it. This ratio is the same no matter how much mass you have. Right? So let's make it simple. If it's parts per 100, let's say we have 100 grams. So if we say we have 100 grams, we have 83.65 grams of carbon and 16.35 grams of hydrogen. Now we can convert to moles. just need a value. So for hydrogen, it's 1.01, right? 0.01. And for carbon, it's 12.01. Now we need a calculator. So 83.65 divided by 12.01 is 6.97. moles. And 16.35 divided by 1.01 is 16.19. Okay, so that's the mole ratio, but you can't write that in a formula, like C with a subscript of 6.97 and H with a subscript of 16.19. It just doesn't work. So we need to convert it. The ratio is established. That is fixed. This ratio of carbon to that many moles of carbon, that many moles of hydrogen. So if we divide both of them by the same number, the ratio is fixed. It hasn't changed. So let's divide this one by 6.97 and this one by 6.97. Right? That one is equal to 1. Right? 1. What's this one equal to? 6.97 divided 2.32. Okay, so now the ratio is this many moles to this many moles. We're close. We need to get that one to be a whole number. Can you multiply this by something to make a whole number? Well, yeah. 0.32 is about a third, isn't it? So 3 times 0.32 will be approximately 1. And 3 times 2 will be 6. So 6 plus 1 is 7. If we multiply both of them by 3, then we get 3 moles ratio to 7 moles. Now we got whole numbers. Notice that rounding here is acceptable because we're trying for the nearest whole number ratio. That means 3 carbon and 7 hydrogen. That's the empirical formula. So I work it out in detail here. Right? Close. Keep going. There you go. C3H7 is the empirical formula for this compound. But we don't know the molecular formula, do we? We would have to multiply this by something. And how do we know what that something is? Well, let's see. Is this problem going to be part of that? I don't want to erase this until we know it's not needed anymore. Right. This one's done with. We're going to do another one and go the extra step to find the molecular formula for the compound. If X is 1, then we've got the formula, but we don't know how to get X yet. So let's do another empirical formula, and then we'll add the bit of piece of information that you need. So let's see, scoot that back. There we go. All right. So now we've got a new problem. This is adipic acid. Adipic acid. I think that's one of the fatty acids that you'll find in true fats, adipic acid, is 49.3 carbon. Now we have 3 elements, and we're given all of them. What if we were only given carbon and hydrogen? How would you find oxygen? Well, just add these two together and subtract from 100. If we know that carbon, hydrogen, oxygen is it, then the one that's left out is just what's left over. So let's do the empirical formula first. Hold on a second. It's like I'm missing something here. Wait a minute. That's not all of it, is it? Okay, I've got some slides out of order, I think. Yeah, I think the last 2 slides are out of order. So we need to find the empirical formula first for this compound. And then let's go to here we go. And then we'll find the molecular formula. You've got to do the empirical first, right? So here's the same problem with the extension added on. All right, so we've got 49.3% carbon. And 6.9% hydrogen. And 43.8% oxygen. Okay, so what do you do first? You assume 100 grams. If you're not given a mass, then you assume 100 grams, which means this is now so many grams. There. Now we can convert to moles of each one. Okay, carbon is 12.01, hydrogen is 1.01, and oxygen is 16. That'll give us the mole ratio, probably in decimal fractions. Let's see, I need another. This one's getting weak. Okay, so 49.3 divided by 12.01 is 4.105. And this is moles of each. 6.9 divided by 1.01 is 6.83. Let me rewrite that. Let's just keep it to 2 decimal places. That's good enough. Okay, and the last one, divided by 16, 2.74. Okay, so now we have the mole ratio of the simplest arrangement, simplest ratio of carbon, hydrogen, oxygen in this compound. But they're not whole numbers yet. So you look for the smallest one here and divide each one through by the same number. That one's going to be 1, of course. 6.83, 2.74. This one is about 2.5. Very close to it. And 4.1 divided by 2.74 is 1.5. Okay, so we need to get rid of those 0.5s, the halves, the fractions. Multiply each one through by 2, and that gets rid of the half, doesn't it? So times 2 this is 3, this is 5, and that's 2. Okay, so our empirical formula would be C3H5O2. All right. Now what we're looking for is that multiplier. Because then we would know the molecular formula, right? And to find out what that is. Well, if we only have 1 unit of this, what would its molar mass be for that? We just add them up, right? If this were 1, then there would just be that many. If it was 2, then it would be twice that many, wouldn't it? Or if it's 3, it'd be 3 times that many. So let's find out what would 1 unit of that be. So 3 carbons, 12.01 times 3. And then 5 hydrogens and 2 oxygens. Gives me 73.08. So 70 would be, this is what I call the empirical weight. Okay? So if we actually knew what this value was and used it to multiply through, it would change this value by whole number increments, would it not? So if we said 2 times that, we would have 146, wouldn't we? So we need another piece of information. What is the molar mass of the true compound? And you have to determine that by alternate means, right? And there are a host of different means to do that that we can't discuss right now. Many of them are what we call colligative determinations that are independent of what the molecule is. You can find the molar mass of a molecule and not know what it is by these procedures. And apparently, one has given them this value. 146 grams per mole is the molecular weight. Same as molar mass. Okay, empirical weight, molecular weight. So how do you find out what X is? Well, if this one is increased in increment each time, then all you have to do is divide this one by that one. And the nearest whole number is your multiplier. So this one divided into that one is 2. X equals 2. Now we can write the formula. C6H10O4. That's your molecular formula. Okay? Okay. You know, I think I've covered everything that we need to know about those other slides.